Hi everyone, I hope you're doing okay. So today we're going to go on to our next topic, which are exponential functions. So we're going to get right to it because this video is a little bit long. We have a lot of information to cover, but it's not difficult. It's just a lot to talk about. So we're going to go right to the work. Okay, so the reason why this is called an exponential function is the form that your equation will have. So notice at the top it says y equals b raised to the x power. So b represents the base of the exponential function, and this can be any number as long as it is positive and it can't be 1. So that means it cannot be negative, it cannot be 0, and it cannot be 1, but pretty much anything else is allowed for b. And then the x is the exponent. So that's why it is called an exponential function, because the variable is part of the exponent. So there's going to be two different types that we're going to look at. If the base is greater than 1, we will call that an exponential growth. And if the base is between 0 and 1, we will call it a decay. So it's going to be one of those two things in each case. Now we're going to take a look at graphs in just a minute, and all of the graphs will have the same basic shape, and they will also have an asymptote. So asymptotes are something that we talked about earlier in the year. They are lines. These will be horizontal dotted lines where the graph comes close to but does not touch as it goes away from the origin. So I'll show you what I mean in just a sec. Okay, so looking at number 1, it is y equals 2 to the x power. So 2 will be the base. So because the base 2 is greater than 1, this one will show a exponential growth. So let's go to the calculator so you can see how this turns out. And you may have seen this before, maybe a little bit in Algebra 1, I'm not sure, depends, but if not, it's not difficult. Okay, so in your calculator, I'm gonna get this ready to go. Can you see that okay? All right, so we're gonna put in 2 raised to the power of x and press graph. So here is the shape that you should be seeing. So notice, first of all, that the graph is rising from left to right. That means it's growing. So you want to look from left to right and see that it's going up. So that makes it an exponential growth. The other thing is it looks like the graph is touching the x-axis right here, but it's actually not. There is an asymptote on the x-axis. So go to the table so that you can see this a little better. If you look on the table, you'll see points like 0, 1, 1, 2, 2, 4, 3, 8. You can plot all of those on your graph, and I would like you to. But look at the numbers that are on the negative side, like -1 is 0.5, -2 is 0.25. What's happening as we go further and further in the negative direction, these numbers are getting smaller, but they're not quite reaching 0. So there's an asymptote on 0. So when you make your graph on your paper, you will need to draw the asymptote, which is the horizontal dotted line, and then fill in the points from the table. So that will be it for number 1. I'm going to do number 2 while we're here and talk about how it compares to number 1. So I'm going to go to y equals and put in the equation for number 2. Oops, I need to go up. Okay, so it is 2 raised to the power of, and it says x plus 4. Now if your calculator is like mine, you'll be able to just type in the x plus 4 in this block, but some of you have a slightly different calculator, so you might have to put your exponent in parentheses, so you'll just have to see what your calculator needs. Then I'm going to press the right arrow to get out of the exponent and then subtraction by 3. So it should look like that. So some of you might have to put the exponent in parentheses. Okay, so transformations are happening between the first graph and the second graph. So for instance, the 2 is the same in both the graphs. So that's not a transformation. That's the base of the function. But then you've got the x plus 4 in the exponent. So what that is going to do to the graph is shift it to the left 4. So that's a transformation rule that we've been studying all year. That'll be a left 4. And then the -3 that you see at the end, that will be a shift down by 3. So again, these are just the same transformation rules that we've studied all year long. So the second graph should go left 4 and down 3, and please write that down. Okay, so then we press graph, and we'll be able to see, oops, wait a minute, I saw that I put an extra 3 on there, so I didn't want that. Sorry, I don't know how that happens. Sometimes make mistakes. Let's see, take off that 3. All right, so here's what it should be. All right, so the second graph, notice, is down 3, and it's also to the left 4. So when you draw this one, you want to put your horizontal asymptote on -3 since it shifted down 3. Then you will go to the table and plot points. And some of them are going to be too high, but you could plot like -1, 5, -2, 1, -3, -1, and so on. And what's going to happen as you go further to the negative direction, you're going to see that the numbers get really close to -3, but not actually reach -3. So that means you will have your asymptote on -3, just like I said. So your graph is going to look basically like this for number 2, but remember you have to put the asymptote horizontally on -3. Okay, so then we're going to take a look at numbers 3 and 4. So notice for number 3, let me get rid of these. The base is a half. So I'm going to put the half in parentheses, just like I see on the paper, and raise it to the x power. So this one has a base of a half, which is between 0 and 1. So this one is going to be called an exponential decay. And if you check out the graph, notice it's the same shape as the other one, but it's going in the opposite direction. From left to right, this graph is decreasing, and we also say it is decaying. Now over here, it looks like the graph is touching the x-axis, but it's really not touching. It is getting close, but not quite. So go to the table, and you'll see just the opposite happening. Like you've got some points that you can plot, -3, 8, -2, 4, -1, 2, and so on. But as you go further in the positive direction down here, keep going, scrolling down, you'll see that these numbers are getting very, very close to 0, but not quite ever reaching 0. So that means your asymptote is on 0. So for number 3, draw this graph, but with the horizontal asymptote across on 0. It's a horizontal dotted line. The calculator's not going to put that. You need to do it yourself. Okay, so then number 4. I want to compare the two. So I'm going to go down here. So notice that there's still a half in the parentheses. And, no, gotta get the 1 in there. 1 divided by 2 raised to the power of, okay, so this one has x minus 1 in the exponent. And some of you may need that in parentheses, depending on your calculator. And then afterwards, plus 5. Okay, so let's talk about transformations. First of all, the half is just the base of the function. That's not any sort of transformation. You might be thinking of a vertical shrink possibly, but not in this case. That's the base. Okay, so then in the exponent, you have the -1. So that means we're going to have a shift to the right 1 in our graph. And then finally, the positive 5 will be a shift up 5. So jot that down, that there would be a shift right 1 and up 5. Your homework will be kind of like that. Okay, so if you check out the graphs now, here we have this. So you'll see that the second graph is shifted up, so that's 5 spaces. That means that your asymptote this time is going to be on 5. So you're going to draw your horizontal dotted line on 5. And then the graph also shifts to the right 1. It's just kind of hard to see, but go ahead and go to the table, and you'll see that there are some points to plot, whatever fits, like -1, 9, 0, 7, 1, 6, and so on. And what you'll see is as you go further down the table, over here, watch the values. They are getting closer and closer to 5, but don't reach 5. So that's where your asymptote lies, on positive 5. So your graph is going to look like this once you plot the points, but with the horizontal asymptote drawn in on 5. Okay, so those are the basics of the graph. So I'm going to go back to the whiteboard now. So now we're going to take a look at numbers, what was that, 5 and 6, and see how these work out. Okay, so these are word problems, and I know everybody hates word problems, but these are actually fairly easy ones. You just follow a formula. So we have two formulas at the bottom of page 1, and they look like this. And they are used when you have an exponential growth represented in the problem or an exponential decay. Now notice there are two formulas, but the only difference between the two is that one of them has plus r and one of them has minus r. And you'll see that there are descriptions of what each of the variables stands for, but I'll go over that right now. These a's right here, that represents the original amount of whatever you're given. The r's represent the rate, like a percentage, but you'll have to change the percentage to a decimal, which we will talk about when we get there. And then t is time, and it's generally in years, but it could be in days or hours or whatever the problem is given. Okay, so you're going to pick one of these two problems depending on whether the amount is increasing or decreasing. Okay, so I'm going to go ahead and go to number 5. So on number 5, it says that we bought a new car for $35,000, and the value of the car decreases or depreciates by 12% every year. So this is a pretty common thing. You can talk to your parents about this. If you buy a new car, after a few years, it's not worth nearly what it was to start with. It does go down in value. So this is a real life example. Okay, so the formula is going to be the one for exponential decay because the value is decreasing for this car. So it's going to be that one. Okay, so I'm going to put in A as the $35,000. That's the original cost of the car. And then this is just the number 1 minus the rate. So it says that the rate is 12%, but you have to change 12% to a decimal. And you do that by moving the decimal point 2 places to the left. So instead of 12%, you're going to use 0.12 raised to the t. Now the t is there so that you can put any number of years in that you need to know. I'm going to simplify this just a little bit more, like keep the 35,000 there, but 1 minus 0.12 is the same thing as 0.88 raised to the t power. So this would be the answer for part A, which asked you to find an equation that could be used to find the value for any given year. So that's A. Now for B, it says, what is the value of the car after 6 years? So all you're going to do is take the number 6 and plug that in for t. So it's going to look like that, 0.88 raised to the t power. Okay, so let's go to our calculator and see how this turns out. Okay, so I want to exit out of the graph. You can press second quit. And it was $35,000. In the parentheses, it should be 0.88 and then raised to the power of 6. Okay, so this number represents the new value of the car after 6 years. Now keep in mind when we use money, we use dollars and cents. So the 14 would be like the cents, and you want to look at the number past the 14 and see that that's 3, and that's not enough to bring it up. So I would say the answer for this would be $16,254.14. Okay, so let's bring that back to the whiteboard. Okay, so the final answer, I'm going to use a dollar sign since it's money, will be $16,254.14. Okay, so that's it for number 5. Okay, the next one is talking about a bear habitat. That would be number 6. And it says that the habitat started with 500 bears and the population has risen by 2.25% each year. So the fact that it says risen implies that this has been growing. So that's an exponential growth. So you would pick the formula that has the R as a positive number. So it would be this one that says exponential growth. So you would just put the 500 bears as the original value A. You would need to put the 2.25% here, but it must be changed to a decimal. So that would be 0.0225. I found that by moving the decimal point 2 places to the left, and then the power will be t. That could be any number of years. And I'm just going to simplify this up a tad and add the 1. So it would be 1.0225 to the t. So this would be the equation that you could use for part A, which is the population of bears after any given number of years. Okay, so for B, all you're doing there is plugging in the number of years. So in this case, it was 15 that they're asking us about. So we're going to plug in the number 15. So back to the calculator real quick. Let's see what we have. Okay, so I'm going to put in 500 for the A. Inside of the parentheses, 1.0225 raised to the power of 15 and equals. Okay, so notice that this is the answer that you should get, but this is a population of bears. So since bears are living things, you would not want to give a decimal answer. So I would say round down in this case because it was only 698.1. It wasn't enough for the extra bear. So I would put down for this one just 698 bears, no decimals. So final answer for B would be 698 bears. Living objects, don't put any decimals. Okay, so those board problems were easy enough. You're just following a formula, so not a problem. Okay, so on the next part, there is a number in math, and you may or may not have seen or heard of this number before, but it is an irrational number, irrational, I said, and it is denoted by the letter E, but it actually stands for a number, and this is approximately equal to 2.71828 and so on. So it's irrational, meaning that it is never ending and it never repeats, kind of like pi, but this is the value that the number E has. So we call this the natural base E, and it's also called the Euler number because the person who invented this number his name was Leonard Euler, and his last name was spelled like this, which you might think is pronounced Euler, but he was German, and evidently in Germany they pronounce that Euler, like with an O. But E is what is used to represent this number. So this number comes about quite often in math for exponential functions. So you will see some exponential functions in the future that have E as the base. So not only in this class, but as you go to higher level maths. Okay, so we're going to look at the first graph. So notice it says y equals e to the x. So that is the Euler number, or the exponential value that's called the natural base e. Okay, so let's see how the graph will look for this. So I'm going to go to the calculator and take a look at it. A lot of moving today, sorry about that. Okay, so we're on the graph part. So I'm going to y equals. So let's erase all this stuff. Okay, so there is a button for E, and there's also one for e to the x. So if you just want the regular letter E, the number E I should say, it's with the division sign, like right over here. But if you want to raise it to a power, it would be on the far left, and I need to move my calculator over a little. It would be on the far left. Do you see where it says ln? We'll discuss what that is in a later video, but right along with ln is e to the x. So that's the one I want to press. Okay, so it's second ln. You'll see it has e with a little block there to put the x in. If yours doesn't have the block, just put e and then afterwards an x. Okay, so when you press graph, you will see this function. Now notice this looks a lot like number 1 that we did a little while ago. And the reason for that is because it's still an exponential function, and it's still an exponential growth because it's rising from left to right. And it's a growth because the base of it is the number e, the natural base e, which is about 2.71828 and so on. So it is a growth because it's more than 1. So you will still have an asymptote on 0, and then you can go to the table to plot points. So in the table, you're going to see a lot of decimals. You'll just have to do your best with that. Like definitely plot 0, 1. This one you could approximate and say 1, 2.7, 2, 7.3. Just estimate those on your graph paper. And then as you go backwards to negative numbers, notice that these numbers get really, really small, but they don't ever reach 0. And that's where the asymptote should be. So your graph should look like this, but with an asymptote on 0, horizontal dotted line on 0. Okay, so while we're here, let's go ahead and do number, I don't know what number this is, but the next problem, I don't have the paper right in front of me. Okay, so after e to the x, the next problem has 3, and then e to the power of, and then notice this is negative x. So put a negative sign and then the x. Okay, so before we press graph, let's take a look at what this would mean in terms of transformations. So the base is still e, still an exponential growth, but the 3 would be called a vertical stretch because 3 is multiplied to the base e. And then the negative x, because that negative symbol is in front, or is part of the exponent, I should say, you would call that a reflection across the y-axis. So please write down those two things, a vertical stretch by 3, and then a reflection across the y-axis. Okay, so here's how it actually looks when you do that. So it would still have your asymptote on 0. It's just going the opposite direction because of the reflection across the y-axis. So go to the table and plot whatever is reasonable. Like you could do 0, 3, and then like negative 1, 8.1, 1 is about 1.1. And as you go further down, you'll see that the numbers get closer and closer to 0 over here, but not quite. So pretty much this graph, but with an asymptote drawn in on 0. Okay, so there's one other thing I want to go over today, and this is an application of exponential functions in real life again. So when you consider banking, exponential functions are used. So I don't know how much experience y'all have with banking yet because you're still young and you probably don't have a lot of money yet, but as you get older, you will want to save for retirement. You'll want to save for your children's college expenses. You'll want to save for vacations or whatever it is that you find important. So you'll want to know, like, how much is your bank going to pay you in interest and how much you're going to get and how long will it take and so on. So there are two formulas that are used in banking that will help you to figure that out. So the first one is given at the very end of the lesson. And this is used whenever the bank advertises that they will compute their interest a certain number of times per year. So it will give a frequency of times per year that they do their interest. So sometimes this will be used. So the A will be the new amount in the account, and this is on your sheet. The P will be the principal, which is also the original amount that you put in the account. That's just the number 1. The R will be the interest rate, which you will have to change to a decimal like we did on the other problems. The N here is what I was talking about. This is the number of times per year that the bank will compound their interest. And this N is the same thing as this N. And then T is time in years. Then there's another formula that you'll see below it. It's P/E to the RT. So this is used when banks advertise that they continually compound their interest. So that means they just keep on compounding the interest over and over and over and over again. And notice that it still has the P, that's still the original amount, the principal, and A is still the ending amount. But look at this, this is the E, the natural base E, or the Euler number that we were just talking about a few minutes ago. So that is a time when this is actually used in the real world, in banking. And then the R is the interest rate and T is time. Okay, so let me just show you some examples. This is the last problem. So we're going to be looking at, it says we're depositing $5,000 into an account. It pays 2% interest, and the balance is after 10 years. They want to know, what is the balance after 10 years? Okay, now it gives several different choices. It says annually, quarterly, monthly, daily, continuously. So that's like how many times per year they're going to compute their interest. Okay, so the first one says annually. So let's go to that one first. Okay, so A is the new amount in the account. We don't know that yet. P is the principal. That would be the $5,000 that we put in there originally. 1 would be just that same 1 in the problem, plus sign. It's a growth. Let's see. R is the interest rate, which it says is 2%. So you'll change 2% to a decimal, which would be 0.02. And in the denominator, it's the number of times per year. So if it says annually, you're talking about 1 time a year. So you'd use a 1 here. Then in the exponent, the n is still a 1. It's the same number as here. And then t is the time, which is 10 years. Okay, so that's going to be what we put in our calculator for part A. But I want to go ahead and set all of these up now so that we can just use our calculator one time and not go back and forth. So the next one is the same information but quarterly. So that means I'm going to change one value only, and that's the n. So instead of 1, quarterly means there would be 4 times a year. So change that to a 4, which also changes the exponent to 4 times 10. Okay, so for part C, it says monthly. So I'm going to keep all the same numbers. It's just that instead of the 4, now I have to think how many months are in a year. Well, of course, there are 12, so 12 would go here. And this would be 12 times 10. So notice the only thing I'm changing each time is the n. Okay, so for D, daily, how many days are in a year? Well, it depends on whether it's leap year or not. 2020 did have an extra day in it, but most years don't have it, so let's not worry about leap year. And say there are 365 days in a year. So then the exponent would be 365 times 10 years. Okay, and there's one more, and it says continuously. So if it ever says continuously, that just means they're going to do their interest over and over and over and over again. And you'll use the other formula containing the natural base E. So that one would be 5,000 E raised to the power of 0.02 times the number of years, 10. Okay, so these are going to be the things that we put in our calculator. So you might want to stop and catch up if you didn't quite yet, because I'm going to put this down and go to my calculator now. Now this is kind of tricky to enter because it's just so complicated of an equation, so be careful when you put it in. Not that hard, but easy to make a mistake, I should say. Okay, so I'm going to erase that. Okay, so here's the first one, annually. So you put in 5,000, 1 plus 0.02 divided by 1 raised to the power of 1 times 10. Now some of you might need to be putting this exponent in parentheses if you had to earlier. So here should be the value that you get. Now this is money, so we want dollars and cents. So I'm going to say $6,094.97 for that one, round it to 97. Now if I don't want to retype all that again, because all I'm changing is just a couple of numbers, what you can do to save a little time is press second entry, which is enter, and it brings up the last problem, and then you can just use your arrow buttons to go back to what you want to change. That just saves a little time. So I'm changing this to a 4, and also this to a 4. Just be careful you change both of the numbers. Both of the ends are now 4 for this one. Okay, so this one would be $6,103.97. I'll just round it to the nearest penny. Okay, so the next one is monthly, so that means a 12. So I'm going to press second entry. Now this one will get a little bit messed up because where I want to change it, it's 2 digits now, but at least it's not typing the whole thing in again. So I'm going to put a 12. You would still need to put parentheses before you go over to the exponent and change this to 12 times 10. Okay, so rounding this one, be careful, it's 99 cents, but notice there's a 7 afterwards, so that means we should bump it up to the next dollar. So it would be $6,106 even. Okay, then I'm gonna do the same thing, but with 365. Back this up. Okay, so again, it's gonna mess it up a little bit because now it's 3 digits, but we can fix that. So it's 365, put a parentheses, arrow over here, and then this is 365 times 10. At least we didn't have to change the beginning of it. Okay, so rounded for that one, you would get $6,106.98. And the last one uses the natural base E. So you would put in the 5,000, use the E to the X button that I showed you a little earlier, E to a power, and it's 0.02 times 10. And press enter. So this one would be $6,107.01. So I'm not going to write this on the whiteboard. I'm just going to stop the video very soon. So y'all, it's come to my attention that not everybody watches the whole video. Yeah. So I want to see how many people actually made it to this point of the video because we're at 32 minutes and I know that's a long time. So I have a surprise for you. If you made it this far in the video, on your paper, the worksheet that you're going to turn in, I want you to put a pi symbol in the upper left-hand corner, just a little pi symbol. And that will tell me that you watched it all the way to the end. And there's going to be a reward for doing that. So don't tell your friends, don't tell anybody, just put a pi symbol there and I'll know that's a secret between you and me that you actually watched 32 minutes of this. So I appreciate y'all who stick with me the whole time. So take care. Bye-bye.